Hi everyone, welcome to the third of 4 videos going through some past exam questions on ionisation energies. So the first question we've got here is a more general one. Just wants to say what periodicity is. So ionisation energy is an example of a property that shows periodicity, and periodicity is just a repeating pattern of properties. That's all we need to say. Right, it's a pattern, but it's a pattern that repeats itself because you get one period, then the next period, then the next period. Okay, so we need to refer to the periodic table, okay? From the first 18 elements only, okay, so we've got to be careful here. Choose an element which fits the following descriptions. An element with an isotope that can be represented as 14 and 6. Right, well, if it's got 6 protons, it's going to be carbon. Okay, we've got our periodic table here. Carbon is definitely the one that's got 6 protons. That's it. No argument. If it's got 6 protons, it's carbon. Okay. The element which has the strongest metallic bonding in period 3. Okay, so let's have a look at period 3. What options do we have? So period 3 is either going to be sodium or magnesium or aluminium, and that's it. Silicon's not a metal. Okay, and as you go across the period, the metallic bonding is going to get stronger. Metallic bonding is the attraction between the ions and the delocalized electrons. Well, aluminium, because it's in group 3, is going to have 3+ ions, so that's going to attract electrons more strongly than the 1+ or the 2+ ions. Okay, so that's going to be aluminium. The element which forms a 3- ion with the same electron structure as neon. Okay, so if we find neon, if it's a 3- ion, then it must have gained 3 electrons to get to the same electron configuration as neon. So we need to go back 3. So it's going to be nitrogen. Okay. The element with the smallest third ionization energy. Okay. So we know, don't we, that as you go across a period, ionization energies increase. Okay. And as you go down a group, ionization energies decrease. Okay, so we're definitely looking at something in period 3. So it's got to be a period 3 element, and we want to be as far to the left of period 3 as possible. Okay, because ionization energies increase as we go across. But if we're saying a small third ionization energy, we need to have at least 3 electrons in the outer shell, because if you've only got 2 in the outer shell, the third ionization energy, the third electron to remove, is going to be much more difficult to remove, isn't it? Because it's going to be in the shell closer to the nucleus. So we need to have at least 3 electrons in the outer shell. And we already said it's period 3, so it's got to be at least aluminium. Yeah, sodium and magnesium are out because they only have 1 or 2 in the outer shell. So we said we want to be in period 3. We've got to have at least 3 in the outer shell, so it's got to be at least aluminium. But then we said ionization energies increase as you go across. So it actually is going to be aluminium. Okay, that's going to be the one that has the lowest third ionization energy. And then the element with the first 6 successive ionization energies as shown below. Okay, so if these are the ionization energies increasing, what we're looking for is where are the big jumps? Where's the big increase? Because the big increase will show when we're going to a new shell. So that's going up by 700. That's gone up by 6,000-ish, 3,000, 3,000, 4,000. So this is the biggest increase here. So between the second and the third. So that suggests that we're looking for an element in group 2, and the third electron is going to be much more difficult to remove. Okay. So if we're looking at group 2, remember we're only allowed to pick from the first 18 elements. So that means it's either going to be beryllium or it's going to be magnesium. Can't be calcium because that's element number 20. So how can we tell these two? Well, beryllium only has 4 electrons, so it can't possibly have 6 ionization energies. So it must be magnesium. Okay. Elements in the periodic table show a periodic trend in atomic radius. State and explain the trend in atomic radius. Okay, so this is from lithium to fluorine. So this is going across a period. And we've seen a question like this before. As you go across a period, the atomic radius decreases. And this is because the nuclear charge increases, because we add one extra proton every time. But electrons are added to the same shell. Okay. And so that means shielding stays the same. So if the shielding is the same, but there's a higher nuclear charge, then the electrons are going to be more attracted to their nucleus. And so therefore the radius is going to decrease a little bit. Okay. So we can then say this means the nuclear attraction increases. So electrons are pulled closer to the nucleus. And that's why the radius decreases. Okay, moving on. Got a few more questions here. So we're talking about rubidium, which is in group 1, and strontium, which is in group 2. They have their outermost electrons in a 5s orbital. What shape is a 5s orbital? It's a spherical shape. That's just a 1 mark thing we need to remember. Right, then they've given us the first and second ionization energies of these elements. Write an equation for the second ionization energy of strontium. Okay, so if it's the second ionization energy, we've already done the first ionization energy. So strontium's already going to be Sr+, and it's going to lose another electron to end up Sr2+, and there's the electron that's lost. And we need to show the state symbols. Remember, the definition for ionization energy is it has to be gaseous. Okay, why is the first ionization energy of strontium larger than the first ionization energy of rubidium? So this is going across the period from group 1 to group 2. Okay, so we're going to talk about the 3 factors that we talk about all the time with ionization energies. It's going to be nuclear charge, atomic radius, and shielding. So across a period, the nuclear charge increases. The atomic radius decreases, doesn't it? It gets a little bit smaller. And the shielding stays the same. So we've talked about all 3 of our factors that we need to talk about. Now we just need to bring them together. So if the nuclear charge is higher and the radius is smaller, then the electrons are going to be more attracted to the nucleus. Okay, so overall, the nuclear attraction increases. So it takes more energy to remove an electron. And then it's asking us, why is the second ionization energy of rubidium larger than the second ionization energy of strontium? Okay, if you notice in the table, it's actually the opposite way around. Look, strontium's first ionization energy is higher, but its second ionization energy is lower. So it's a bit strange. Well, actually, no, it's not strange if we think about it. Strontium is in group 2, whereas rubidium is in group 1. Okay, so when you take one electron away, when you're then taking away the second electron from strontium, you're still taking that electron from the outer shell. So it's relatively easy. But for rubidium, once you've taken one electron away, you've then moved into the next shell down. So you're now much closer to the nucleus. The radius is much smaller, and there's going to be much less shielding. So it's going to be much more difficult to remove the electron. Okay. So this is because the second ionization energy of rubidium removes an electron much closer to the nucleus So there is a stronger nuclear attraction. And it requires more energy to remove. Okay.